You know I love Star Wars. And I love physics. And, Star Wars Ahsoka. I guess it's a spoiler, but there's a scene. It's on YouTube, too. I actually got this video online. And let me just play this part of this video, and I won't even say I'll say as little as possible. But come on, if you were going to watch it by now, you would have watched it. But still, this is a pretty good clip. Let me switch to this other version, the YouTube, the QuickTime version, because I'm just going to scroll through it. So here, I'm not going to actually play it. So that's Ezra, and he jumps. He's trying to jump to this Star Destroyer, which I just realized is moving. Huh. I like that. Okay, that's moving. That's fine. I didn't analyze that. I need to do that later. And he's not going to make it, so Sabine gives him a little force push, and there you go. Okay, so the best part of this is right here. Since things aren't really moving, then especially this platform right there is not moving. So I can use this as an example for video analysis. I'm going to do a video analysis for this, and the second part in two parts, right? Because the second part right here where they switch cameras, now the camera is moving. So we're going to have to use calibration point pairs, and this is a great opportunity to show you how to do that. So I've already got Tracker loaded right here. I want to show you how, if you haven't used Tracker Video Analysis, just search Tracker Video Analysis. I'll put a link down below. Super great program, free, runs on Mac, Windows, Linux. It runs online. I don't really like the online version, but it does work. So I have my students use this. They don't have to install anything because it is a Java program. Let's get to it. Let's analyze this. Okay. So the other thing that we have here, if we have a video analysis, I can mark the location of Ezra in each frame. And I can get the time from the time between frames. But the X, Y, and position, I need to know the size, right? I need to know the size of something in the thing, and I don't have that. I mean, I could probably try to find the length of Ezra, but he's so tiny in the picture. If I knew this floor width of a Star Destroyer, then I could use that. But the other option, there's three things. If I have projectile motion, like I do here in this part, then I have three things. I have the scale, I have the time, and I have the vertical acceleration. So if I knew the vertical acceleration and the time, I could find the scale. If you know any two of those, you can find the third one. So yes, it's not on Earth. I'm just going to assume it has an acceleration the same as Earth. So let's just get started. I'm going to start off with, I'm going to put my coordinate system down here, right at the corner, right there. Okay. Now, I need to pick a scale even if it's wrong. So I'm going to go up here to this and click New Calibration Stick. And it puts this little blue stick right here. And it says 1. But I want to pick something that I can find again later. I'm going to pick this length right here. I'm going to try to get it lined up with the motion of Ezra. Because things that are further away have a different scale than things that are closer, right? Just like I can squeeze my own head and my camera down here, right? That's the same idea. And if the camera, quote camera, because I know this is all fake, I'm not that guy. I know this is fake. If the camera is really far away, then the relative distance between this and the back doesn't really matter. And I'm going to count on that, even if it's not true. So let's just do this. So it's right now set at 1, right? I don't know how high that is. What I'm going to do is mark the location of Ezra in each frame, look at the acceleration, and then change that to get the correct acceleration. I'm going to assume it should be negative 9.8 meters per second squared. I'm going to assume it's on Earth. It's not on Earth. I've already said that. And I'm going to say it again. Okay. So now what we want to do is go up to Track, New, Point Mass. And it's going to change the screen a little bit. That's fine. And all I need to do is to mark. Oh, I'm going to do this too. This is on. Oh, I got it already started on frame 0. If you want to, if you have the whole clip in there, sometimes it's easier to go up here, click the clip settings, and click the start frame to the one I'm on. I'm on frame 0 anyway, so it doesn't really matter. Which I'm kind of surprised. So now I'm going to click this again just so it's highlighted. To mark a location, all I need to do is hold down the Shift key and you can see my cursor changes. So I'm going to mark it in the middle of Ezra, but he's so tiny it doesn't really matter. If I click that, he's going to move a little bit, and then I just keep clicking, and I should have thought this out beforehand, but I can do this pretty quickly. It's not that many frames. And we could talk about stuff, right? We could talk about how I think Star Wars is awesome, and I apologize for looking down like this, but it's just super tiny the way I got the screen so I can screen capture it. We can talk about my billions of blog posts that I wrote on physics of Star Wars. I have done, I just love Star Wars. So, and I know it's not real, and that's fine. It's not even science fiction, really. Is it science fiction? I don't know. Because I got to keep going. I mean, it's not really based on any scientific principles. I mean, the Force is not scientific. I mean, if you said that Star Wars was space fantasy, I'd be all on for that. Okay, that's it. So we switch. Now, let's look at, I'm going to do this in a little bit, but if you look at this horizontal position, you'll notice that it's very linear, and that's exactly what we'd expect with projectile motion, right? When something's in the air, the only force is the downward gravitational force, so there's nothing pushing it this way. The velocity should be constant. I don't know how the force works. I'm assuming that he gets a boost when he force jumps. It's from his jump, not from when he leaves the ground. He pushes himself, not while he's in there. I could be wrong. George Lucas, let me know. Dave Filoni, let me know. Call me up. Call me. Let's talk. I would love to be involved in Star Wars in some part. It would make me so happy. But let's look at the Y motion right here. So I'm going to click on this and go to Analyze. And you see it's slightly parabolic. One of the things, whenever you see these points like that are the same, it's usually because the original frame rate has been changed to another frame rate and you get these frame doubling. It's fine. Don't worry about it. So let's just fit a quadratic equation, curve fitter, parabola. Okay, right there. So there, it's a fairly good fit. But you'll see here the acceleration is negative 1 point. This times 10 to the negative 1. So let me write it right here. Switch to the camera real quick, just as a review, in case you can't remember. So this is my kinematic equation. Y equals y as a function of t is y0 plus vy0t plus 1/2 ay t squared. So I'm fitting y equals a t squared plus bt plus c. So I get these coefficients a, b, c. So this would be 1/2 that. So if I want a to be 9.8, then a would be 9.8 over 2, which is 4.9. So that's what I want. Okay. So I want this number to be negative 4.9. I can do that by going back over here and changing this. Let's just go back so we can see. And you see it is the star destroyed it. I didn't analyze that. I'm so excited to do this now. So I'm going to click on this. I'm going to guess. Let's say it's 20 meters. And you could solve this. I just like to guess because I don't want to solve it. Now I can go back to my graph, which went where? There it is. And you'll notice it's negative 3.8. So that's better. Okay. So I just need it a little bit bigger. Let's try 25. I think I did 23. I think I did 23.5 before. Negative, okay, 23.5. Let's try that. 23.5. Okay, it's getting closer. 23.7. No? Okay, let's go up to 24. 24. No? Okay, let's do 25. Getting closer. 26. Okay, there. 4.9. So now I have the acceleration. And let's just go back over here. Now I could analyze this. Right-click on this. Click Analyze. And I don't know why it does this, but it'll show both of the graphs here. I just want this. See, I want a line there. So there's my slope. And it looks like, if you see, it's kind of small, negative 1.73, but it is, there is an E. I'd want to zoom this. Let's see if I can do that. It is times 10 to the 1. I just cut off. I could stretch out the whole thing. Oh, I can. Let's stretch this out. I'm going to stretch this. There. There's that times 10 to the 1. So it's 17 in the negative x direction. I could also get the initial y velocity from the parabola, but that's that. Okay. Now let's jump over to the next important part. If I go back to the video right here, you see I don't have, you'll notice that the camera moves, so I'm going to need to take into account the camera motion and in order to get the motion of Ezra right here. And that's really important because, let's see, wait. Yeah, because, oh, this is the part I want right here, actually. Right there. That's the part I want to get. Now, you'll notice this stuff in the background. I'm gonna scale based on that, which may or may not be a good idea. But I'm looking at this. I want the distance from here to this black thing. I'm going to use that as my scale. Okay, so let's go back to tracker video analysis, and I want to measure that. We can see that same thing from here to there. So I'm going to pull up this tool, new tape measure, and I'm going to measure it. So I'm going to put that right there, and it doesn't have to be perfect, especially here because I'm doing a video. And it says 15.11. So I'm going to use that to scale, even though I think it's wrong because it's further away, right? Well, further away would be this way. But it's the best I can do. We could try to do a better job, but I think this is going to be fun. So let's go let's do a new file, new tab. I'm going to load that file in there again, right there. Okay, and then I'm going to skip forward to the force push right here. Let's see. Skip. I think I might have cut that part out and just had, okay, right here. It's not going to be perfect. Now you'll notice that I'm going to move this up a little bit. Frame 126. So I'm going to set this frame, start frame to 126. Next, I'm going to go to coordinate system. And I'm going to uncheck fixed origin. I'm going to uncheck fixed angle. I'm going to uncheck fixed scale. They may change, they may not. I don't really know. Now I'm going to go to calibration stick, new, and I'm going to use this right here, so that just like I did in the other video, to there. And what did I say it was? Oh my gosh, 15.1. So let's go to view, just jump. 15.11. Okay. View. So 15.11. Okay. Now, there is another option. I could look at his motion after the push and again find the acceleration, but I'm not going to do that. I really want to show you this calibration point pair. So how do I take into account the motion of this frame and still get data? And here we're going to use this awesome tool called calibration point pairs. So I have the thing scaled. I'm going to go up here to this tool, the same one I used to make the calibration stick, and new calibration points. So what this does is it gives me I can mark the locations in the background frame in each frame, and it will adjust the motion of the axis. And I can move the coordinate system. I'm going to leave it right there. So I'm already ready for those. I just need to click on the 2 points. I'm actually going to use those same 2 points. I'm going to click right here. I'm going to click that little corner thing right there. Actually, I'm going to use this piece right here. It doesn't have to be the same as the scale. Okay. Now, I'm going to go over here. And this can get a little tedious. It's fine. Tediousness is fine. And you can't see it. That's fine. I'll put it right here. I'm going to skip forward 1 frame. And you'll notice that my points here moved. So all I need to do is drag them back to where they should go. Drag this back to where it should go. And now I'm going to do my next frame. Drag it. Drag it. And you'll notice the coordinate system is moving and the scale changes too if it needs to. Now that was a doubled frame. Drag it. It doesn't have to be perfect. Just has to be good enough for perfect. And again, and I don't know if you want me to do this whole thing. I'll show you the result in just a second. I have all the data. I did this already. I wrote a blog post for this, which I will post, even though it's behind the Medium paywall, and I apologize for that. I had it free for a little bit, but you know. Okay, you're getting the best parts anyway. Another double frame. One more. Now, this motion keeps going, but now if I go back to the beginning, you'll notice that they stay where they're at, and I can go to track, new, point mass, and I can track the motion of him, and it takes into account the motion of the background, which is awesome. So I just click, and then it keeps moving. So there you go. Okay. Let me show you the data for that. Okay, that's what I'm going to do. And then I'm going to show you my VPython model for this, which I've already built. So here is the blog post. Let me move that out of the way so you can see. If you want to read this, you can. If you can read really fast, that's that same first graph I got. There's my velocity, horizontal velocity in the first part of the jump. And then, oh, this is fun too. So one of the things you can do is to create this, what's called a worldview. Let me show you how to do this. If I go over here, I need to drag this up a little bit. And then as I play through this frame moves so that it can see the whole thing. And you can export that as a GIF. If you go to File, Export, Video Clip, and then go to Worldview, and you can save it as a GIF, and I think that's awesome. And that's what I did there. So that's that. So you can see that's the forest jump, and the Star Destroyer stays stationary, even though I think it's moving, right there. And then here is the horizontal velocity during that time. Here's the vertical position. That's the horizontal position. The vertical position, you can see he is accelerating up. So you can find the acceleration and use that to find the force. If you assume his mass, you could find that. And that's kind of cool. Okay, now let me show you I will show you this at the end. I'm going to show you that in a second. The homework questions. I'll go over these homework questions because they're kind of fun. You can answer them even if you don't have this blog post. Going to the video analysis, not the model. Let me just run this for you, and I'll show you some of the tricks for building this. So here's my Ezra model. There's the platform, there's the side of the Star Destroyer, and there's the jump. And I try to make it as accurate as possible. I don't have all the data, right? You don't see him the whole time. We don't know how long he's in the air before he gets pushed. We don't know any of that stuff, so I had to guess. Now, the tricky part is putting the locations of these boxes, right? Because a box in Web VPython gives you define it based on the center and the dimensions. So if you want to line up these edges like that, then you have to do a little bit of trickery. But other than that, what I'm going to do is start off with initial velocity and position for Ezra. I'll let him move along. And then during this time that Sabine's pushing on him, he has another upwards pushing force. And so he's going to change his motion. And then he goes back to projectile motion right there. Let's look at the code. Edit code. Let me just go over some of the highlights. I did use 2 Gs because I did one. I was just doing some calculation stuff before. So this is my vector G, and then that's another G. This is my initial velocity that I got from video analysis. I just wanted to know the angle that he launched at. I don't know why. It was in the blog post. This DTF is the time that Sabine, of the force. That's how long Sabine's pushing on him. And this is that force. That's the acceleration during that time that Sabine's pushing on him. That's the mass of Ezra. This is the force of Sabine, the magnitude. Here's that platform where he starts his jump. So it's a box, and I wanted to put it like, I know the distance that he jumps the whole thing, right? Because if I go back over here, that's kind of cool. Let's go to just jump right here. Now that I know the scale, I can drag this over here and say, okay, well, how far horizontally did he jump? Right there, that's what, like 72 meters. And how high up did he go? Well, that's 34 meters. So you can get that data. That's the platform. So then I pick the size, just the size of the box and the position, so that that corner would be somewhere where it would be visible. I could have put it at the origin, but when you do that, then you have all this empty space on the side that I didn't want. Ezra is a sphere, and I tried to. This is to make sure that he starts at the corner of that platform box, using the dimensions. And I could have used variables, but I didn't. I made him way too big. He has a radius of 1.1 meters, so he'd be 2.2 meter sphere, which is not true, but it just makes it so you can see him better. And then he's yellow and he has a trail. The Star Destroyer, which is DS, Death Star. I don't know why I put DS. It's also a box, and then I find its position based on the position of Ezra plus those other dimensions. So I'm actually measuring from the corner where I start, which makes it a little bit easier. But then you got to find, you got to use its size and the location. It's tough, but it's art. That's art. There's my initial velocity, momentum, time step, the time of the jump. This is the time before the Sabine's force push. I guessed at that, right? I guessed at that because you don't actually, it flips back and forth, and I don't know if that's real time or not. So this is just your normal numerical calculation. Calculate the force, update the momentum, update the position, update time, and then during the force push, I just change my force. So it's got that force from Sabine right there, and then it's pushing up. I assume it's pushing up, and then that's that. And then I go back to just normal force, and that's it. So it's kind of artistic. I like it. You can jump, you can rotate this around. I did not, like I said, take into account the motion of the Star Destroyer because I didn't notice that until just now. So I do want to look at that, but that'll be something else. Last thing, homework questions, and I'll try to repost these in the comments, because that's what I love about this. You could show this to a student, they could be interested in it, and they could answer their own questions. There's too many questions for me to answer, so suppose Ezra's going to jump to the same initial angle. How fast would he have to jump with his initial velocity so he would not need Sabine's help? That's kind of a good one. Jump over one. Oh, so what about if his force jump lasts for 1 meter distance? Then what's his force push, and how's that compared to Sabine? What about the power for both Sabine and Ezra? What about air resistance? What if you add air resistance in there? What changes? That's a pretty fun one, right? Because you can say he's kind of like a human skydiver, but he's moving in a direction. You can estimate the drag parameters by looking at skydivers, and that's pretty fun. And then what if Sabine was off by a little bit? So there you go. Okay. Video analysis really is a great example to use these calibration point pairs in Tracker to show you how to do that. I have an older video, and I just need to redo it. So hope that helps, and I'll see you later.